What I'm going to do today is talk about some research that we've been doing in the area of wireless and mobile networks. And before I start, I want to acknowledge basically a lot of people that have helped with some of the work I'm going to present. It's truly a group effort. If there are any problems, they're all mine, though, if you find any. So let me first of all, explain basically what the title is. So as you will see later on, I'm very much bothered by kind of the legacy or the constraint of terminology, and I find sometimes terminology kind of conjures things in our minds that is probably not the right thing. So as a result, when I talk about networks, wireless and mobile networks, I want to call them something different than what most people have called them. And you'll see the reason should be clear as we go through this. So I will use WAM, wireless and mobile, as the acronym for wireless and mobile networks as opposed to anything else. So the first thing is that I like to think of wireless and mobile networks as sitting in a continuum. So as you probably already know, but also I will explain, there are lots of varieties of wireless and mobile networks that people have addressed or talked about or researched in the past. The problem has been that we have been hard to kind of find relationships between these different types of networks. And that has caused, I think, significant confusion over time. So I like to think of them as basically networks in a continuum, basically a large space with really no natural boundaries except what we impose and what we draw ourselves. And so I'm going to talk about this WAM continuum as essentially a space, and I'll explain, we'll see this picture again and I'll explain exactly what it is, but basically think of a space of networks. And then you come and tell me my network has this kind of features and these parameters, and I will basically place it in this continuum. And the idea that you can then, within this continuum that may not have natural boundaries, you can draw boundaries. And you can tell me this particular network falls in this type or this class. And within this class, it's appropriate to use this kind of routing or run these kinds of applications and so on. So I think thinking about this continuum and thinking about how we might draw boundaries within this continuum is going to help us deal and operate these networks. So let me kind of tell you a little bit about kind of the goals of what I think this continuum gives us. It gives us a way to talk formally about networks. So as you'll see, people talk with terminology. They have some kind of conceived or preconceived notions of what the networks look like, but they're not formal. And so it's very hard for us to actually talk about them amongst ourselves. Often we will run into networks that are really hard to classify. So it's important to actually understand when you get hybrids of networks. Sometimes a network will look like a certain type of network for a while, and then for various reasons, changes in mobility pattern caused by changes of days or changes of applications will cause it to look something different. So we can understand this motion or adaptation of network over time and kind of adapt our operations to it. Okay, and you'll see also it tells us a little bit about performance. Okay, so let me actually kind of start really a little bit early, and some of you are already experts in these topics. But bear with me if some of this looks really familiar. So I will start really just slowly, and then I will go very quickly over something that we did that kind of gives us a clue of the relationships, and then I'll delve into this WAM continuum framework. Okay, so let's talk about the two types of networks that people have dealt with. The first one is what has come to be known as mobile ad hoc networks, or MANETs for short. And these are networks where you can think of nodes as sitting in some space, and you also think of the network as connected. So if you take a snapshot of the network, you look at it, it's connected. So there is a path from every node to every other node. These links are wireless links. But because there are paths, we can route data in the traditional way, that we understand from wired networks. We find a path and then, build routing tables and move the data around. The idea is that because these are mobile ad hoc networks, the nodes, of course, can move. And because they move, the paths that used to exist are disrupted. And then basically what happens is the mobility causes the paths to change. A lot of these protocols that are built for mobile ad hoc networks, for MANEs, detect this and recover and find a new path by repairing essentially the path. Okay. So just to summarize this MANE paradigm, the network is connected. It's kind of a good engineering trick that we take a network that we don't know how to deal with, reduce it to something we know how to route on, and then apply our traditional techniques. The path exists, but it could be, it has to exist for a long enough period of time to actually make any sense. Otherwise, you can't route over it. But if it's disrupted, it can be repaired. And the most important thing to understand here, and I think this is kind of known to people that work in this area, that basically in these networks, even though mobility or mobile is the first part of the acronym, actually mobility is an error. It's an error condition. All these protocols work with this mindset that if there is a mobility, there is a route error that gets returned. So something went wrong. Of course, you can't call something mobile and say if you move, you're doing something wrong. You know, so it starts with the wrong mindset, and then there's actually the notion of a route repair, which addresses these route errors. So although there is mobility in these networks, we don't like it. Okay, it's kind of a strange kind of expectation on our part. Now, recently people have talked about another type of network, which are I'm going to call them intermittently connected networks, but they go by a lot of other names. And they're really also wireless and mobile, but they seem to also appear in situations where it's very hard to insist on long-term connectivity and kind of rare mobility, where mobility basically is so prevalent that the connections cannot be long-lived and have to be intermittent. So if you take snapshots of these networks, and I'll give you examples of them, they're basically disconnected, sometimes by necessity, or sometimes by design. You turn down the power so the range is not long enough, and so you don't get the connectivity that you would get otherwise. But they're mobile. And in fact, in these kinds of networks, mobility, as you'll see, becomes our friend. Because basically, we like mobility, and mobility is what gives us the data connectivity, the ability to move data around in the networks, which is, again, a different mindset. There's lots of other names that show up in the literature, and there may be minor variations on what they mean, but they're all kind of intermittently connected networks. Delay tolerant, disruption tolerant, sparse, opportunistic. Okay, so the main paradigm of routing there is a little bit different. So while in the MANEs, what we appeal to is our knowledge of wired networks and the way we store and forward data in a wired network, here we do things a little bit differently. Because we can't have the connectivity. So what we do is we can forward data to a node and store it for a while, but then mobility helps us. So the node might have to carry the data around for a while and then find the next opportunity to move it. And this mobility, this store, carry, and forward is the paradigm that gets us to move data in these networks, even though they might be intermittently connected. So here's an example. This is a famous routing protocol called epidemic routing for these kinds of networks. It's I'll give you an example here. A bunch of nodes. They're mobile. There's data that's sitting at a source that needs to move to a destination. And there is really there are some wireless links that form occasionally as nodes meet each other, but there are no paths in this network that you could use that exist in any snapshot of the network. So as nodes move and they get close to each other, they detect this neighborhood proximity, and the data then can be moved. Because it's epidemic, it's a very simple forwarding algorithm. You just infect or move your data around to every other node that you meet. And essentially, it's a flooding or a broadcast algorithm. The data eventually makes it to the destination, which is our objective. But then we have this other problem of lots of replicas of the data, which we can deal with by using timers or hop counters or something to kind of kill extraneous data. There are lots of people that have thought of systems like this where mobility kind of help you. I'll give you some examples. This is something that's called shared wireless infostation model, where basically you strap sensors on whales in this case, but any kind of animal, and then as the whales meet each other, the sensor data gets propagated, and eventually it reaches some kind of collector, but basically through mobility and getting close to this connector. Another example is this DACnet. This is actually something that was built in India. The idea basically is you have these villages that don't have internet connectivity, and then you have the big city that is very well connected to the internet. And what you have is you have these mobile entities, trucks or motorcycles or whatever, that go and sit next to a kiosk in the village, collect data from that that has been submitted. Could be email, could be videos, it could be pictures. They collect that data and then move around. Eventually, they come back to the city and then they dump the data into kind of the internet and then collect data back and then move it around. Okay, so again, this is mobility kind of helping us move the data around. Here is another example. This is two cars moving on a highway. The front car, the Beetle in this case, wants to talk to the back car, but they're too far away from each other. So one thing they can do is watch for traffic coming in the other way, give the data to the car moving in the other direction, and as the car moves, eventually it will meet the car in the back and deliver the data that way. Right? So again, this is mobility helping us move data around. Here's another example. This is from work that we've done maybe a few years ago. This is actually an interesting question of we have a highway and we have two roadside entities. These are actually fixed stationary entities. On one end, I have essentially a router with good internet connectivity. On the other hand, I have an ambulance that's farther down the road in a place where basically there is really no good internet connectivity. There's perhaps an accident or something, and there is an X-ray or some test result or whatever that was taken here and needs to be transmitted to a doctor over the internet, but there's really no channel at this point. So the idea that we explored here is what can you use the cars on the road as a channel to move the data. So I'll give you an animation here that shows. So basically, the data gets sent to these cars and then gets deposited as the cars reach the router. Eventually, when the whole file, and this is a fragment file, is reached, then there's kind of an acknowledgement message that goes back and says the file has been received. Lots of details here, but basically, again, this is using mobility to move data. And in this case, we actually use the cars as a channel, and it's interesting to think about what are the properties of that channel and so on. A last example is something that we've been exploring for a while, is this idea of message ferrying. And the idea is that you have mobile nodes possibly in the environment, but then you have one of the nodes has some specific mobility properties that makes it kind of explore the area or traverse the area that you're dealing with in some kind of coverage. It gives it some coverage. And so what we can do is declare that this node is what we call a message ferry. Okay, so its job becomes to move data around in this environment. And so there's really no, even if there might be contacts between the nodes, but there's really no data being transmitted between the nodes over these contacts. What happens is every node waits for the ferry. So everyone knows who the ferry is. And so when they see the ferry, and the ferry approaches, they actually give it the data. Okay, and of course the ferry is moving around, and eventually the ferry makes it to the destination, and then the data is delivered that way. Okay, so this is actually similar in some sense to this DACnet picture that we saw. However, the granularity of data transmission is really at the message level as opposed to waiting for bulk data to kind of be accumulated and then deposited. And then the nodes that are sources and destinations of data here could also be mobile. So you don't have stationary villages and so on. Okay, and we'll come back to this in a second. So let me kind of talk about this intermittently connected paradigm. in my opinion, the intermittently connected paradigm is really, when we started thinking about wireless and mobile networks, we really should have started thinking about that, instead of thinking about the Manet paradigm, which assumes the network is connected and well-behaved and mobility is kind of rare, and when it happens, I can fix it. Okay. The reason I think, and you know, I'm just as guilty as everyone. I mean, when we worked in the Manet environment, it was very appealing because we could kind of visualize a wired network after we dealt with all the wireless issues. Once we have that, we declared the problem solved, as any good engineer. And then slowly people discovered that really mobility might be more, and so none of these solutions really work. So I feel this is a really good paradigm. It's been a fertile ground for a lot of good research. You know, we have to rethink a lot of different things, okay? But the question I want to kind of also address here, is this really a new territory? I mean, are these kinds of networks truly that different from the first type, the Manet networks, to the extent that we really kind of had a revolution? And my argument will be, again, come back to my initial premise, is that we're really looking at two extremes in this case of a continuum. And the question is, when does a Manet stop becoming a Manet and become an intermittently connected network? It's actually a very important question because it tells you that you should stop using this kind of routing technique and move into this other routing technique. But we actually don't have the language to talk about this, and this is kind of my goal to do this. So let me kind of step back, though, and show you, go back to the message ferrying, and I'll show you that really message ferrying, again, if you think about it, is not a new paradigm. And people have thought about it to a great, you know, there's been a lot of literature on something very related in wired and wireless networks. And that is this notion of a connected dominating set. So the idea here is this. If you know, basically, if you take a network, in this case, it's a stationary network, but people have applied this to Manets. Manets, again, there is mobility, but it's not it's kind of a rare event. And so you can always appeal to wired network results from that. So connected dominating set essentially is a backbone. Typically, it's a tree. And there are properties. Basically, the connected dominating set is a set where all the nodes in it are connected. And then every other node that is not in it is actually one hop away from a member of the connected dominating set. If you have that, you can do routing easily. Basically, all you have to do is find a member of the connected dominating set, and then hop your data to that. And then within the connected dominating set, because it's connected, you can move data, and the routing typically there is easy. And then you move it to the element of the set that is closest to your destination, and then hop the data down. Okay, so, and people have done a lot of research on this. Even in Manets, how do you actually figure out what the connected dominating set is in a distributed manner, how you should adapt it if there is mobility? Again, the idea here is it has to be slight mobility. You can't have things moving all the time. So this has been done. So it turns out that if you think about it, although we didn't really see this until much later in our research, that a message ferry is essentially a single node connected dominating set. And then you can also think about having multiple message ferries in a network. So I'll give you an example. Typically, we think of a message ferry as a network, as a node that, by virtue of its own mobility, has some good coverage properties. So I mean, these are examples of kind of vehicles, for example, and people that actually, when they move, they have good coverage properties. Sometimes it's not totally random how they move, and they move in a large area and make contact with a lot of other locations. And so you can think of these entities as forming a connected dominating set, but now it's mobile. The elements of that set are moving. So if I think of this bus as a ferry, the police car as a ferry, and this delivery truck as a ferry, then I can hop data around. All I have to do is I'm sitting here by the fountain waiting. I wait for the bus, then the data is delivered. Now I need to reach I guess this is a bank. The bus doesn't go to the bank, but the bus moves around enough that it can reach this bus stop. And maybe there is a point at that bus stop, and I can deliver the data to it. The police car makes rounds and eventually would come close to the bus stop, and I can hop the data this way. Eventually, the police car comes in contact with the delivery truck, and it can hop the data this way. The delivery truck will reach the bank. Now, if you think about this, this is essentially like the connected dominating set, except that the elements of the set are moving. And they again have to have some properties, you can formally talk about it, that are not just spatial in the graph in terms of what we think of connected dominating set, but they also have kind of time properties that over time they do certain things. So I'm not going to give you the details of this, but we have formalized this concept basically and shown that you can talk about these nodes as essentially what looks like a connected dominating set. Formally, though, it's a generalization. It's actually truly a generalization to the point that the connected dominating set is really a special case of this. So in fact, when we run our algorithms, if things don't move, what we get back essentially is a connected dominating set heuristic that produces a good connected dominating set. I'm going to kind of spare you some details, but basically we have algorithms and we have formalisms to talk about this. Now the point that I want to make here is this. This is a mobile network that is really intermittently connected. What we are able to do is find something that is a generalization of a connected dominating set. So that tells me these two networks are related to the point that if one is not moving or moving slowly, then it looks exactly like the other one. Okay. So now the question is, how can we talk about this more formally? Let me, this is a good point for me to show you what I want to show you here. Hopefully this is well behaved so that you will see. So what I have here is actually, I want you to look at this, and I'll keep them all up rather than put them all. So these are actually simulations of mobile nodes, okay? Let's look at the top corner here. Here what I have is few nodes running in an area. They're actually moving, but they're moving very slowly, okay? There is a defined range here, and so nodes that are within that range form a link, but a node that's far away here cannot actually talk to any of them. Now this is a canonical kind of disconnected network, all right? It's moving, it's not moving enough. There is really no way to get data from, if I pick an arbitrary node pair, I cannot guarantee that I can move data between the two ends of that node pair, okay? So this is a truly disconnected network. Now the thing is if you look on the right side here, the top right, this is the same network. The only thing I've changed is the speed. These are the same set of nodes, they're just moving faster. Okay, and this is what the kind of the intuition, sometimes counterintuition, that in this case mobility actually helps me. We've kind of lived in the world where I hate mobility and it's an air condition, but clearly in this environment, if you look at mobility, I actually occasionally get paths. They don't survive very long, so they're not usable in the strict as a path. But I get enough connection that I can do this store, carry, and forward to move the data around. Okay. Now, if I take this speed is very low and this speed is 1, this is 0.001, sometimes something happened in the middle. And in fact, there are lots of gradations. It's not like, it doesn't happen kind of all of a sudden. There's slowly, this kind of network becomes this kind of network, which is a very nice kind of network. Okay, let me move down here. This is exactly the same network. The difference, though, is I have 20 nodes instead of 5. The range is the same, the speeds is the same, and everything. Now, this is a network that a wired network engineer loves, because it's moving, not moving very fast. Actually, it's not moving at all. And I think it's just the simulation is slow, but it is moving. I mean, as you can see from here, we love this kind of network. We can establish routes, we can run distributed routing algorithms, and we know exactly how to deal with it. This is a case, though, when if I take the same network and move the nodes faster, it becomes problematic. I can't, there are paths. This network is essentially always connected. However, these paths don't live long enough for me to actually do anything with them. So in fact, I have to hop the data the same way I would hop it here, with a store, carry, and forward to make it effective. Okay. The problem, though, I mean, when I talk about these, I can describe these things to you qualitatively. The question is, how do we actually talk about this? Okay, what is the mechanism? So if you get nothing from this talk except that basically what we're trying to do is give you a way to kind of talk more formally about these kinds of networks, the spectrum from a left to right kind of thing over time and so on. So let me go back to the. Okay, so So let me kind of go back to this. So let me kind of reiterate where we are. And in this case, I'm going to, rather than talk about two networks, I'm going to talk about three types of networks. Okay. The first one is the manets, which is we already talked about. These are well-behaved. They don't move a lot, and so on. DTNs, or intermittently connected networks, are networks that they move, and they move enough so that I can actually get connectivity. I can't do it over paths, but I have to hop the data and carry it. But if you think about it, there's actually a third class of networks. We don't think of them as networks because they're not connected, so they're not really networks in the strictest sense. But there are no paths in them, and there's no way to hop the data and carry it. But I'm going to call them sparse or disconnected networks. This is one of the networks that we saw on the top left. Basically, there are nodes and some links, but there's no connectivity end-to-end because there's no mobility and not enough nodes. So really, there are three classes of networks that we can think about. And the question is, what are the relationships between these? And then how can we talk about, if I tell you this network has these parameters, can you tell me where it belongs? OK. So we talked about the purposes of this. So let me kind of go back. And in order to do this, we have to talk about paths. And we normally talk about a network path, but we talk about a space path. That's the traditional path. This is a path, if you take a snapshot of the network, you can actually see the path. Instantaneously, it shows up. All the links in the path are contemporaneous. They all show at the same time. Then we can talk about a space-time path. And a space-time path is a path that exists, but only if you run the movie. If you just take a snapshot, you don't see it. You see one hop in the path, maybe two hops in the path, but the rest of it is not there. But if you run the movie, you'll see one link form now, then you'll see one link later, and one link later. Okay? And it's very important to realize that basically one is a special case of the other. A space path is really a special case of a space-time path. There's really, the one that's most general is the space-time path. And just to give you an example of this, here is if I take this is a network, a bunch of nodes, and the links come and go over time. You can see basically this green path. This is a space path that exists at a point in time. But we have these space-time paths that I can trace over time, eventually delivering data from one end to the other, although these two ends are never connected at any instant in time. Okay. So now let's see how we can talk about, and I'll give you a qualitative kind of feel for this, and then kind of summarize how we get to this formally. But the qualitative thing is actually the most interesting part. So here is a space, and on the x-axis I have node density. On the y-axis I have mobility. Node density is how many nodes there are in the space. Mobility you can think of as speed, how fast they're moving. Okay. On the corner here I have low density and low mobility. Here I have high mobility and of course, so high density and low mobility, and here I have high mobility and low density. If you think about this corner for a second, I have not very many nodes and they're not moving very fast. What you end up with is this picture that we saw of essentially a disconnected network. Okay. The question really is that, okay, right at this corner it's disconnected, but if I increase the density a little bit and increase the mobility a little bit, it's probably still disconnected. Now, arbitrarily we might feel like we want to draw a line somewhere and figure out where that line is, and so that's what happens. So I think of these networks as networks with no paths. You can't get from every place to every other place. Okay. Now let's take that on the x-axis and move up here, low density. Low mobility and high density. Okay. What you will find is these are great networks because nothing is moving. They're not moving very fast. But then there's a lot of nodes, and so there's a lot of potential for contacts. And so this is a great network. We love these networks. These are networks that have very stable paths that we could use very easily. Okay. And these are networks that have essentially space paths. Exactly when the space paths start forming, and it's kind of fuzzy, right? And of course, if you move up, you continue to have it. Then, to make a long story short, you can have other types of networks that have space-time paths, and then you can have networks in the middle that we, maybe call them hybrid networks that have some node pairs or have space paths, some node pairs don't have them, and so on. Now, why is this important? If I can develop this space and I can tell you my network is here or here, I can kind of determine what kind of routing I use. So, for example, if a network has space paths, in this area I can use what I'm going to call space path solutions, but these are basically what we do in wired networks. These are typical easy to route over networks that have stable paths. And now, in this part, though, pretty much everywhere, I can use a space-time path solution. So think of the epidemic routing that I showed you, where you kind of infect everyone you meet, and eventually the data makes it to its destination. I can use everywhere here, including networks with space paths, of course. It's not maybe the best way to do to route data that way, but you can certainly use it here. You cannot use, however, epidemic routing in these networks. The ones that have no paths, actually, even epidemic routing doesn't work. There's not enough movement to get the data to percolate everywhere. Now, we think of other kinds of solutions, which we call no-path solutions. And these are solutions where, for example, you add a node as a message ferry. Okay, there's not enough mobility, so you add node with some mobility to move the data around in this space. Okay. Now, what is important to realize is this no-path solution really is designed for this corner of the space. But in fact, because it's a general enough solution, it will work for any network. If it can work in this no-path network, it will work for any network, clearly. So you can deliver data that way over these networks. Okay. So now how do we talk formally about this? And maybe I'll try to kind of capture the essence of what we have here. But basically, we start off with this theory of evolving graphs. Okay, and there's a reference here, but I think others have also looked at it. The idea basically is, rather than think about a graph as a graph with fixed in time links, you think of the links as being intermittent. They have an on-off kind of property, and they come and go over time. And so you can really think of your graph as a snapshots of different graphs over time, maybe with the same nodes even, but different links over time. And in this literature, people have talked about something they call a journey over this graph. A journey is really what we've been calling a space-time path. It's really a way to move in the evolving graph, but you never see the path you move over in any one instant in time, but over time the path forms. Okay, so here's an example. This is an evolving graph. It looks different. It's the same set of nodes, but the connectivity looks different over time. And it's, there are instants in time where you can talk about it as in each instant it's a disconnected graph. And then you can find a journey or a space-time path from one node to the other over this. And there's been work with algorithms, developing algorithms for these kinds of graphs. So then what you can do is you take this formalism and talk about connectivity of node pairs. So what we have here is three kinds of node pairs. So if you think about this, a pair is an S pair is if there is a path that exists from the source to the destination. Okay, it's a space path. So if I take a snapshot of the graph, I actually see the space path in the network. A pair of nodes is a space-time pair if there exists a journey between one node, from one node to the other over time. It doesn't exist at any point in time, but over time I can find this journey or space-time path. Okay. Now we can also talk about this journey as being of a certain duration, that it exists if I can do it in 20 minutes, but I don't really care for journeys that take 40 minutes or 30 minutes, right? So we can also add the element of time to defining a space-time path and its existence. And then there are these N pairs. Basically, these are pairs that you cannot connect. It could be that you cannot connect ever. You cannot talk from one to the other ever. Or it could be you cannot talk over a 20-minute period. So I give you a 20-minute window, you cannot reach from A to B. But maybe over 30 minutes you can reach, but I care about 20 minutes. So in that case, this pair I cannot connect. Okay. So, you take any specific node pair in the network, and it kind of changes over time. So basically, you can take a pair, and over this window, that actually, because of the way the network is, there is actually a space path between them. So over this period of time, I can route over them in a traditional kind of wired network way. But then, in the next time period, all of a sudden, that path that was there is no longer there, and there's enough mobility, but I can move things around, but I still need to kind of hop it and carry it from one node to the other. And then over another window of time, these two nodes could be totally disconnected. Okay. And we have, detailed formalisms in our work. It's not really, important to kind of get into the details here at this point. What we have been able to do is actually this: take these definitions, take some parameters that we input into, for example, how long do I care to have a journey? Is a journey 20 minutes fine, and so that may be my limit, and then anything beyond that I classify as it doesn't exist, and so on. And you input it into some network classifier, and you produce some results. So I'll show you some results here. This is, some of you are familiar with the Haggle trace. It's a 9-node network that people have collected contact traces over. And we basically use this trace. This is the period, almost 100 hours of time where contacts are connected, and there are 72, I think, node pairs that we look at over time. And basically, the color coding here is blue is space path, green is space-time path, and red is no path. And what you see here is basically there are a lot of node pairs, and there's some diurnal pattern, in fact, showing up here. At night, a lot of node pairs basically are disconnected. You can't get from one to the other. This is a well-known kind of artifact of this particular data trace. Some people were roommates or something, and so they were actually, their devices were close enough at night that there was always a space path between them, right? They were good friends even in the morning when they had coffee together and stuff. But you get also this period of space-time connectivity, but it's actually striking how much red there is. In fact, these networks are known to have really bad connectivity properties. The people have studied them, analyzed them. But this is a way to visualize really what's going, and it's at the node pair granularity. You can look at node pairs. There is symmetry here. In fact, each node pair shows up twice because the direction is really important here. So that's why you get this and this are really the same node pair, but it's the opposite, the destination. Okay, you can do other kinds of things. You can actually talk about the classification percentage. Take any particular node pair, and you can see that over it's the lifetime of the trace, the node pair is 20% well connected, maybe another 20% space-time connected, and another 60% there is no connectivity. So you can talk about that, and you can look at changes as you allow for longer journeys. So if you think a longer journey is okay, your application allows you for longer journeys, you will see that the amount of red here decreases. So essentially there is less disconnection in the network because you allow yourself more time to reach the destination. So it turns out really the connectivity in these graphs is very much a function of what you call good connectivity, especially over time. Okay, so now you can take this node pair classification, and formalism allows you to kind of talk about networks as a whole. Okay. And we've used this terminology basically of the network as a whole as either a space path network, which is a network that's always well connected, all node pairs are well connected. And unassisted DTN, as this terminology comes from earlier work, is basically a network that has space-time paths between all node pairs. You don't really it's not connected instantaneously, but over time it's connected, and the journeys are short enough to actually qualify. And so we have unassisted DTN. Then we have these assistance needed DTNs. This is basically networks where there are some node pairs where there actually is no path. Either the journeys are really long, so they don't qualify, or there are no journeys over the lifetime of whatever window of contacts we consider. Typically, we talk about the 100% type network, which means we insist that all node pairs have this property. But then you can talk about partially connected networks. For example, you can say, I will call a network well connected if only half of the node pairs are well connected, or 75%. It depends really on what you desire. So our framework kind of allows you to specify that as a parameter. So here is an example of how you might look at the network. And this actually now, if you remember the sketch I drew, but this is really now kind of a more formal way of visualizing this. Again, I have the number of nodes, and I have a mobility parameter. In this case, it's the average speed. And here I have color-coded. The red is a disconnected, no-path network. We don't like these networks. The blue is a network that is very well connected, stable paths for all node pairs. The 100 here means that all the node pairs are of that variety. Green is where I have journeys that qualify, but I don't have stable paths. And what you see here basically is, like we predicted, in this corner you have this disconnected region. What is interesting is that, and visually you can almost see this, the details of how we did this is that the network kind of slowly, and these are simulations, so it's, you get percentages of networks, so the color red kind of decreases and the green takes over. And so you get regions here where it's sometimes green, sometimes red. It's kind of a mixture of the two colors. And really where you draw the boundary depends on how strict you are about the property that you're looking at. So this becomes really more of an application or operator kind of question of exactly where you draw the boundary. It's clear the corner is red, it's clear this corner is green, but where the boundary is. And this is what I meant by a continuum. There's really no easy way to talk about this without talking about other things that you care about. What is interesting is if I relax my requirement from being 100% to 50% of the node pairs having a certain property, I get a lot less red, and I start getting some blue, basically. In this corner, I have good connectivity, but only for 50% of the node pairs, not all the node pairs. Okay, so what good is this? So we've actually looked at it, other than actually giving us a way to think about networks. We've looked at a bunch of applications. One interesting one is that it actually gives you a way to think about performance. And this is a way to think about, and on the x-axis here I have some classification of connectivity, essentially the percentage of connected pairs. On the y-axis I have some data delivery performance, how good my delivery is, and how much data do I lose. And what you'll see is a really good correlation between our classification number and how well the network does in data delivery, and this both for short journeys and long journeys. There's another way another thing to use with this, another application for this kind of formalism, which is it can get you very quick. Remember, these are not actually simulations. It's network classifier. It's not actually a simulation where I have to run for a long time. It's a very quick, graph kind of centric algorithm. It just looks at the graph over time. It doesn't actually simulate anything. So these are very quick ways to look at networks. So here, for example, is a way where I took a network and then I put a ferry in the network and added the connectivity provided by the ferry. And what we'll see here on the right-hand side, I have, the details are perhaps not as important as basically think of the red here as being disconnected. And when I add the ferry, and this is, we don't like networks like this, as when I add the ferry, I have only a small portion of red. Basically, the network is mostly connected no matter how many nodes I have in it. But there's only a small part of it. But it's kind of easy to visualize now that adding the ferry has improved your connectivity in the network, okay, without actually having to run a significant simulation. Okay. So we've done other applications, and we have a paper that just came out in January in the SIGCOMM CCR journal that basically talks in some more detail about this. So let me kind of wrap up. I think as the community has started thinking about wireless and mobile network, I think we started, for any good engineer, and maybe the good point, because we talked about networks that are appealing to us and that we understand really well. Okay, kind of reduce the problem to something we can work with. I think, but as you think though about applications for wireless and mobile network, you think that intermittent connectivity is really more natural for these networks and allows you to use them in more contexts, right? And so I think that the migration to that kind of network is interesting. What I think we came to realize in our work, and I think others have reached very similar conclusions, but we were able to talk about it more formally, is that these intermittently connected networks, really, they're not different, they're just more general. I think if you think about it that way, there's really no issues. It's just a more general network. And what is interesting, because it's more general, it makes it possible that if something applies or is useful in an intermittently connected network, it will also apply in the less general context. I mean, as that is implied by the generality. So what is interesting is that anything we develop for intermittently connected networks is also very applicable to networks that are not intermittently connected. Okay, and more importantly, if a network is sometimes intermittently connected and sometimes not, you don't really need to change. As long as you apply intermittently connected kind of methods for routing, then it will continue to work when the network is connected. Now, of course, if the network becomes connected and stays connected, then you probably want to do something different. But if the network is moving between these two over time, it's probably better to do the more general, and that will work all the time. If you're familiar with the song New York, New York, so if you can make it there, you can make it anywhere. So basically, these are the kinds of networks that we're talking about. Now, and this comes from my own kind of personal experience that people that have worked in Manet, and I count myself among them, are very defensive in the sense that they think that because we've already addressed mobility in Manet's, there's really nothing to be gained by looking at this other kind of network that has more intermittent connectivity. It's just a change in parameter. But in fact, it isn't. It's really there's a fundamental difference. On the one hand, it is a fundamental difference, but on the other hand, the reason we can't really see that is because it's everyone will draw the line in a different place, and it's really a continuum. So that's why it's very hard for us to see that things have changed, because if I draw the line, as you saw, really, there's really no easy way to think about a network changing from one type to the other. It's kind of a continuum, and it moves slowly from one to the other. So I think if we realize this, we won't have to fight over this anymore, and it's just might as well talk about the more general case and understand that we're talking about a continuum. Okay, so thank you for your attention.
Thank you very much. Are there any questions? I guess they want us to use this one.
Okay.
So I was wondering if in your classification of networks there was not a dimension missing. It's not really important, the existence of a path from a node to a destination in a given interval of time, but it's also the capacity that you offer. So, and this could really change the picture, right?
Sure, absolutely. And the way we envision this framework is really it's just a multidimensional space, and you can put whatever dimension to it that you care about. So the idea is not to restrict you. I've shown you 2 dimensions, and I've talked about easy ones just for us to be able to visualize this better. But you can think of capacity as a dimension. We've done some work on power. For example, how much power is in a particular node as another dimension, and so you can think of any dimension you want. In fact, in reality, these networks probably are some n dimensions, and the regions are complicated-looking things that, and capacity certainly is one of them. Although we have not done anything to formalize capacity, but you can think of adding capacity as one of these dimensions, either dropping one and you still have 2 dimensions, or adding a 3rd dimension and then you visualize it that way.
Actually, my question was almost in the same line. I was going to ask the same thing about adding another dimensionality when you consider how long the nodes were in contact with each other, rather than looking at what percentage of the network was actually connected in terms of pairs. You had 50%, 100%, and then adding another dimension on top of it, saying that how long.
So you can talk about like contact volume, for example, which is a cumulative, the number, basically cumulative contact time, the contacts plus time, each contact times its duration, basically, and you sum that. That gives you a contact volume, and you can classify a node pair according to how much contact volume it has. It's I can call it adequate, inadequate, okay, and make that as one of your dimensions, and then you can. You have to formally define though. I mean, the exercise we went through in connectivity, we talked about these 3 types of of node pairs. For contact volume, there may be 2 or 3, depending. You can say, this is a high contact volume, medium, low, and the threshold depend on your application. High contact might allow you to send a video file. Medium contact allows you to send an email, for example, and low contact is useless. There's not enough bandwidth or contact volume to send anything. So, and that depends on your application. Then you can take that the way I just described it and apply the same formalism. The classification now will be, again, very algorithmic, but it will be a little bit different algorithm because you're looking at somewhat different criteria.
Any more questions?
It was an interesting presentation. Thank you. You did a lot of analysis in the sense of. Yeah. Okay. Thank you. Thank you. You explained to us this continuum, which allows us to understand this. Thank you. Thank you. Thank you. Right. The next thing would be obviously to apply this to engineering, and you already mentioned that maybe one could do routing and then adapt that routing to these different network connections. And can you elaborate this a little bit, and maybe also talk about maybe other networking functions which you could address in this way? Yeah.
So I'll give you an example. And we've considered this, although we haven't finished this work yet. But basically, the question is this: if you can think of maybe the network speed or something due to diurnal patterns gives you a network that is maybe in the green or in the blue region most of the time. Okay. But as you observe things, you could actually be observing data delivery performance and so on. You decide that the network has become disconnected, that either the mobility has changed, radio range might have changed, or something has changed. So now the data is not being delivered. And so that puts it in the red region. So as the node moves in the red region, then you might apply you might have a ferry, for example, ready to go. And you say, okay, now, someone asked about robots last time. So you can have a robot available and you say, you go, okay? And so it goes around in the area and now it starts delivering data, okay? And then...
But now you're switching up between algorithms, which is
one
state here,
well, we have to have a hysteresis, of course. I mean, what you do is, of course, you don't switch on a very hard threshold. Hysteresis basically is what you have to use. You make sure that you switch maybe easily, but don't you switch back until something basically starts working again for sure. So that avoids oscillations, and so there are always issues like that clearly with that. But that's one way to do this adaptation. And my thought here is that you could use the classification algorithm as the way to determine when you should adapt. Okay, again with the understanding that you have to have a hysteresis so that you don't adapt back and forth all the time. Right. So that's how we would think.
So I like the idea of these evolving graphs, that they also have this temporal component, the time dimension. And I was wondering whether it is it's possible to, let's say, have a kind of a graph theory where it allows you to conclude if two graphs are, that they have also this temporal component, if they are similar or not, so that you can say, for example, that if your benchmark, let's say your routing mechanism or your protocol has a certain performance at a small graph, you can sort of like generalize the result on a more, in a larger graph. If, of course, you can prove that you can sort of like transform the small graph to the larger one, or if these two graphs are similar.
Yeah. I think, I mean, you hit on something really, I think, interesting here. That there is probably a lot of theory to be developed for these evolving graphs. All we know about regular graphs, we can probably perform on these evolving graphs with some changes. I mean, the example I gave you on this, the connected dominating set, it's a well-known connected graph theory. And if the graph is disconnected, in fact, there is no connected dominating set. It does not exist. And if a graph is connected, you know, it's a well-known concept. It's known to be NP-hard and so on, to find it. And so people have studied this forever. Now, what I've shown you actually is the connected dominating set for an evolving graph. In fact, that's exactly what I described earlier on. So you know, but there's tons of other concepts. You know, concepts of you know, power law graphs. What is a power law graph in an evolving graph? I mean, because you don't. You know, the number of neighbors instantaneously might not have that, but over a window of time, you might have a power law kind of property. So there's a lot of theory that can be moved. I mean, you know, I think this is just an endless mine of kind of research topics to kind of take what we learned about graphs to move them into evolving graphs. You know, personally, I'm not a graph theorist, so I just whatever I need, I try to figure out. But the rest, I think maybe others would be interested in.
So thank you very much again.
Thank you.